In this lesson, we will discuss the various ways in which lateral control about the longitudinal axis of the aircraft is achieved. The aircraft rolls about its longitudinal axis. Lateral control about this axis is primarily achieved by ailerons. There is an aileron on the trailing edge of each wing. The ailerons are operated by the control column or yoke. The ailerons are flap-type controls, but their angular movements are in opposition to each other. When one aileron is angled up, the other is angled down. Consider the aircraft in the graphic. The left wing has the downgoing aileron. This will increase the camber and increase lift. The upgoing aileron on the right wing has a reduced camber, so its lift will be reduced. The lift forces are now out of balance, and the aircraft will roll to the right. It will continue rolling to the right until the ailerons are returned to the neutral position by the pilot. Movement of the control column or yoke is instinctive. If the pilot wishes the aircraft to roll right, the yoke is rotated right. Rotate the control to the left, and the aircraft will roll left. An undesirable side effect of the use of ailerons is adverse aileron yaw. The increased lift on the upgoing wing gives an increase in the induced drag, whereas the reduced lift on the downgoing wing gives a decrease in induced drag. The difference in drag on the two wings produces a yawing moment, which is opposite to the rolling moment. That is, a roll to the left produces a yawing moment to the right, and a roll to the right produces a yaw to the left. There are three main methods in common use to counteract this adverse yaw. They are differential ailerons, freeze ailerons, and aileron rudder coupling. We will now have a look at each of these methods. With differential ailerons, the aileron linkage causes the upgoing aileron to move through a larger angle of deflection than the downgoing aileron. This increases the parasite drag on the upgoing aileron and reduces it on the downgoing aileron, thus reducing the difference in total drag between the two wings. Freeze-type ailerons achieve the same balance in drag by having the leading edge of the control surface designed so that it extends below the lower surface of the wing on the upgoing aileron, thus increasing its drag. The downgoing aileron leading edge remains shrouded and produces less drag. Some aircraft may employ a control system using the principles of differential and freeze ailerons together. These are known as differential freeze-type ailerons. Not only does the upgoing aileron travel further than the downgoing one, the leading edge of the upgoing aileron also extends into the airflow. In the aileron rudder coupling system, the aileron and rudder systems are interconnected, so that when the ailerons are deflected, the rudder automatically moves to counter the adverse yaw. The ailerons are normally situated at the wingtip to give the greatest moment for the force produced. However, this also means that they cause the maximum twisting and bending loads on the wing. As the aircraft speed increases, this can cause a loss of effectiveness, or even reversal of the aileron. To reduce these effects, the ailerons can be mounted further inboard. Alternatively, two sets of ailerons are often fitted, one set at the wingtip for use at low speeds when the forces involved are low, and one set inboard for use at high speeds when the forces are greater and could cause greater structural distortion. On some aircraft, with both inboard and outboard ailerons, both sets are used at low speed. But once the flaps are retracted, the outboard ailerons are locked out, and only the inboards operate. On others, the outboard ailerons are used in isolation until the flaps are retracted. The system then switches to the inboards only. The trailing edge flaps, which are discussed in another lesson, and the ailerons, both occupy part of the trailing edge of the wing. For good takeoff and landing performance, the flaps need to be as large as possible. And for a good rate of roll, the ailerons need to be as large as possible. However, space available on the wing trailing edge is limited, and one solution is to droop the ailerons symmetrically to augment the flap area. They then move differentially from the droop position to give lateral control. This method is used throughout the Airbus fleet. Another system uses the trailing edge movable surfaces to perform the operation of both flaps and ailerons. Such devices are known as flaperons. They are shown here on the SkyStar Kitfox. Spoilers are devices for reducing the lift of an aerofoil by disturbing the airflow over the upper surface. Their use is fully covered in another lesson. They are normally considered as secondary flight controls. However, they are often also used to assist the ailerons and occasionally to replace them by reducing the lift on one wing but not on the other. Raising the spoiler panels will disturb the airflow over the wing and reduce the lift. When a roll is instigated, the spoiler panels on the downgoing wing will deploy, while those on the upgoing wing will remain stowed. Unlike the aileron, spoilers cannot increase lift, and so a roll maneuver controlled by spoilers will always result in a net loss of lift. However, the spoiler has several advantages over the aileron. There is no adverse yaw. The raised spoiler increases the drag, and so the yaw is in the same direction as the roll. Wing twisting is reduced. The loss of lift is distributed across the chord, rather than being concentrated at the trailing edge. It does not suffer from the phenomenon of flutter. Flutter will be explained in a later lesson. Spoilers do not occupy the wing trailing edge, so there is more space available for trailing edge flaps. On some types of aircraft, rotation around two of the axes may be achieved with one control surface. For instance, the elevon, a combined elevator and aileron, is used on tailless aircraft to give both pitching and rolling control. The ruddervator is the name of the control surfaces on the empennage of a V-tail aircraft, which combines both pitching and yawing control. The stabilator is a movable tailplane, combining the functions of horizontal stabilizer and elevator. One of the few airliners to use a genuine stabilator was the Lockheed TriStar. That is the end of the lesson. Here are the important points you should take from it. Spoilers may be used for roll control. Remember that the panels on the downgoing wing will deploy, whilst those on the upgoing wing will remain retracted. Inboard ailerons are used to reduce wing twisting for high-speed flight. The outboard ailerons are normally disabled when the trailing edge flaps are fully retracted. There are a number of methods used to counteract adverse yaw, the most popular being differential ailerons. With this system, the upgoing aileron moves through a greater angle than the downgoing one, to equalize the drag on the wing.